Yeah, welcome. So we are discussing the various CPU scheduling algorithms. In the last class, we have discussed the priority scheduling algorithm. Today we'll be moving on to the next CPU scheduling algorithm, which is called as round robin scheduling algorithm. So basically this algorithm, how it works in the sense, it assumes that the ready queue as a circular queue. It considers the ready queue as a circular queue. So So that is a ready queue is considered as a circular queue, but still it has a beginning and a end. Maybe you may say this as the start of the queue. If this is the start, then this point will be the end of the queue. And the round robin scheduling algorithm, what it does in the sense, so the ready queue contains like this. Okay, it can hold certain number of processes or jobs. Okay, so and it is a circular queue. So the algorithm, the scheduler, what it does in the sense, it will pick up the uh, job which is at the starting end of the queue. It will pick up the job which is at the starting end of the queue, and that job will be assigned to the CPU, and that job will be assigned to the CPU, and CPU will execute this job for some quantum of time, for some quantum of time. So the time quantum will be specified. Okay, so we call the time quantum as q. We call the time quantum as q. The value of q may vary from 10 milliseconds to, typically, I'm saying there is no hard and fast rule. Typically, q ranges from 10 millisecond to 100 millisecond. Okay, or it depends. So it means that if a process gets the CPU, it will execute for that much millisecond. Okay, let us assume 50 milliseconds. In our case, let us assume Q as 50 milliseconds. So what happens in the sense, whenever a process gets the CPU, it will use the CPU only for 50 milliseconds. Before that 50 millisecond, if the process itself terminated, then it will uh, give up the CPU. Okay, it will release the CPU, and again the operating system will go back to the queue and identify the next job which is at the start of the queue, and it will start processing. Okay, this is the case if the process terminates before the time quantum expires. Okay, but assume that a process is not terminated until this 50 milliseconds of time. So it is still using the CPU, but the time quantum 50 millisecond is over. Once this 50 milliseconds time quantum is over, a timer interrupt will be triggered. A timer interrupt will be triggered, that stating that the time quantum for this process is already completed. So 50 milliseconds is over. So immediately once that 50 milliseconds over, the operating system will take up this process, and it will keep it in the end of the queue, and it will keep it in the end of the ready queue. So this is the ready queue. We are assuming we are considering it as a circular queue. Okay, so this is how this algorithm works. That is, every process will get an equal amount of time quantum to use the CPU. Before the time quantum expires, if the process completes, uh, then obviously it will release the CPU, and it will go out of the system. If the time quantum does not expire by that time, then a timer interrupt will be triggered, and the operating system will preempt that particular job. The operating system will preempt that particular process, and it will move back to the end of the, or the tail part of the ready queue. So like this, the the scheduler continues until all process completes its job. Okay. So basically here every process will get an equal amount of CPU time, and that time we call it as time quantum. Okay, every process will get an equal amount of CPU time, and that is called as time quantum. And typically time quantum will be equal to 10 to 100 milliseconds. If there are n process in the ready queue, assume there are n process in the ready queue, and and the time quantum is q, and the time quantum is q, then each process will get 1 by n of the CPU time. Then each process will get 1 by n of the CPU time, and no process will be required to wait no more than n minus q time units. Okay, so these are some of the uh, characteristics of round robin scheduling algorithm. If there are n processes in the ready queue, and if the time quantum for each process is q milliseconds, then each process will get 1 by n of the CPU time, and no process will be required to wait n minus 1 into q time units. Okay, let us see this with the example. Assume n is equal to 5. So it means there are 5 processes in the ready queue. Currently there are 5 processes in the ready queue. Okay, let us assume q as 20 milliseconds. That is, each process is going to get 20 milliseconds of time quantum whenever they get the CPU. Each process will be getting 20 milliseconds whenever they get the CPU. That is the time quantum. Okay, they will be executing for 20 milliseconds. Okay, so now you can plug into this particular formula. So like what is the maximum time a process may have to wait for the next round of execution? So it is just n minus 1 into q. So in our case n is 5, so n minus 1 is 4. So 4 into 2 is 4 into 20 is 80 millisecond. So a process need not wait more than 80 millisecond for getting the CPU during the for the next round. Okay, so it will be either after 80 millisecond, it is sure that it will get the CPU, or before 80 millisecond also it may get if some of the process completes in between. Okay, so basically this is what this particular thing says. And what are the limitations of round robin algorithm? The limitation is, if the value of q is very large, if the value of q is very large, then round robin algorithm will become a FIFO algorithm. That is first come first serve algorithm. FIFO is nothing but first come first serve. Both are same. Okay, you can call it as either first in first out or first come first serve algorithm. So if the value of q is so large, then the round robin algorithm will reduce to an FCFS scheduling algorithm. Okay, assume the value of q as 500 milliseconds. Okay, then what happens in the sense, if a process gets the CPU, then it is not going to release the CPU before 500 millisecond. So it means it is more or less equal to an FCFS scheduling algorithm. Okay, if the value of q is very small, if the time quantum is very small, say q is equal to 1 millisecond, 1 millisecond, then what happens in the sense, most of the time the CPU will spend in context switch, which will increase the overhead of the processor. Okay, so the overhead will become too high if the q value is very small. If the q value is 1 millisecond, then what will happen? CPU will execute a process for 1 millisecond, again it will context switch, it will take the next job, it will execute that for 1 millisecond, again it will context switch. In that case, probably the time it spends on the context switch will become more than the actual processing time or the execution time. Okay, so these are some of the limitations of round robin algorithm. So we have to identify a good value of q so that the algorithm works in an optimal way. Okay, so now it is good to make some comparison. So if you see FCFS algorithm, FCFS is a non-preemptive scheduling algorithm. That is, if it gets the CPU, it won't leave until it terminates or get into wait state. I mean IO wait. But if you see the round robin algorithm is a round robin algorithm is a preemptive algorithm. Round robin algorithm is an The round robin algorithm is a preemptive scheduling algorithm. So whatever we are discussing in today's session, round robin algorithm, it is a preemptive scheduling algorithm. That is, FCFS works only in non-preemptive fashion, and round robin works only in preemptive fashion. Okay. So how, what you can say in the sense, round robin can be called as a preemptive version of FCFS. Round robin can be called as the preemptive version of FCFS. That is, FCFS also always takes the first job from the queue and it executes, follows the order. Okay. Round robin also follows the same order. But the only difference is FCFS is a non-preemptive algorithm and round robin is a preemptive scheduling algorithm. So we can define round robin algorithm in this way also. That is, and round robin algorithm is a preemptive version of FCFS scheduling algorithm. Whereas if you take the other two algorithms, shortest job first and priority scheduling algorithms, those two algorithms can work in both ways, in both modes. Either they can work in preemptive mode and also they can work in non-preemptive mode. Okay. So these are some of the things which you should know. Okay, fine. Now let us understand how the round robin algorithm works with an example. So let us assume there are three processes in the ready queue, P1, P2, P3 in this order. P1 at first, then P2 and then P3. And this is the CPU burst required by each of the process. P1 needs 24 milliseconds, P2 needs 3 milliseconds, and P3 needs 3 milliseconds. And the time quantum Q value is 4. That is, each process will execute for 4 milliseconds of time once they get the CPU. After the 4 millisecond is expired, then a timer interrupt will be triggered and the operating system will preempt that process and it will bring a new process. So this is the scenario. So considering this scenario, let us try to calculate the average waiting time and average turnaround time for this particular list of processes. Okay. So we are using round robin algorithm. So time is not given. So it means we have to assume that all process comes at time 0. All process arrived at time 0 and it arrived in this order. So first P1. So first P1 is in the ready queue. So the scheduler or the dispatcher will first pick the job P1 and P1 will be given to the processor and P1 will execute for Q quantum of time. Here the value of Q is 4. Okay. So in our case, the value of Q is 4 milliseconds. So P1 is going to execute for 4 milliseconds, 0 to 4 millisecond it will execute. Okay. After that, operating system will preempt. So the remaining time left over for P1 is 20 milliseconds. It has to execute for 20 more milliseconds. Okay. Then the operating system preempts to the process P2. Now the control goes to P2 and P2 needs only 3 milliseconds, but it can use up to 4 milliseconds of quantum because the quantum time is 4 milliseconds. So after 3 millisecond, that is at 7th millisecond, process P2 will release the CPU. Process P2 will release the process CPU because it no more needs the CPU. Now again the operating system will check who is next in the ready queue. So the next process in the ready queue is P3. So P3 will be given one one quantum of time. That is one quantum here is equal to 4 milliseconds. So P3 will execute for is allowed to execute for next 4 millisecond, but it needs only 3 milliseconds. That is at 10th millisecond P3, sorry, this is P3. At 10th millisecond, P3 will release the CPU. At 10th millisecond, P3 will release the CPU and again operating system will check in the ready queue which is in the ready queue, which process in the ready queue. So now P1 has P2 has completed, P3 is also completed. So these two processes already finished. So only P1 is in the ready queue which is waiting. So only P1 is in the ready queue. So P1, so now the operating system will assign P1 to the CPU. So P1 will execute for next 4 millisecond, that is up to 14th millisecond. Again, operating system will check, is there any other process in the ready queue? No. So again P1 will continue. P1 will continue. So after 14 millisecond, it needs, after 14 millisecond, it has remaining 16 milliseconds. Okay. So again, it will continue up to 14 plus 4, 18 millisecond. So after 16 millisecond, the remaining time left over is 12 millisecond. Okay, then again it will continue up to 22 millisecond. Okay, P1 will continue up to 22 millisecond, but as there is no more process in the ready queue, P1 will keep continuing. P1 will keep continuing. So 22. So that is after 22 millisecond, the leftover is 8 millisecond. Okay. So again it will continue up to 26 millisecond. Okay, so after 26 milli, sorry, after 14 millisecond, the leftover is 16 millisecond. After 18 millisecond, the leftover is 12 millisecond. After 22 millisecond, the leftover is 8 millisecond. After 26 millisecond, the leftover is 4 millisecond. Okay, so next one more slot it will take. So again, as there is no more process, again P1 will continue and it will complete at 30th millisecond. Okay, so here you can see 14 to 40. So it has continuously used the CPU from 10th millisecond to 30th millisecond, that is 20 millisecond, and here it has used for 4, which is 24 millisecond. Okay, so this is how the Gantt chart is going to look for this particular set of process using round robin scheduling algorithm with a Q value of 4. So this is the Gantt chart, and from this you can calculate the average waiting time and the average turnaround time. So the average waiting time is 5.67 millisecond and the average turnaround time in this case is 15.67 millisecond. So this is as usual how we calculate. So I guess you can calculate by yourself. Okay. So if you see the performance of round robin scheduling algorithm, it has a better performance. It has better performance, but obviously its turnaround time is less than SJF, because we know that SJF provides the minimum average waiting time and the minimum average turnaround time. So it is not the best algorithm, but it performs reasonably good. Okay. Now let us consider some features of this particular algorithm, round robin algorithm. So as we already discussed, the selecting appropriate value of Q, that is the time quantum, how much it should be, it is very crucial in round robin scheduling algorithm. So let us discuss that with an example. Assume the ready queue contains only one process. Assume the ready queue contains only one process and that process needs 10 milliseconds to execute. That process needs 10 milliseconds of CPU burst to execute. Now assume the value of Q. Let us assume different values of Q and see how it behaves. If the value of Q is 12, the quantum time unit, if it is one quantum unit is equal to 12 millisecond, that is if a process gets the CPU, it is going to use for 12 millisecond. Then in this case, what happens? If this process gets the CPU, then it will keep on using the CPU, and then it will keep on using the CPU for the entire duration of the particular time, and there is no context switch. There is zero context switch. Okay, there is no context switch at all. Consider the other case. So initially I said there is only one process, but that is not the case. It can have more than one process also. Okay, let us assume not as single process. Let the queue contain some process, but this is the first process. So now it is executing for this much time. Okay. Now let us assume the time quantum is reduced to 6 milliseconds. If the time quantum is reduced to 6 milliseconds, then what will happen? First, this particular process will execute for first 6 milliseconds. After that, there will be a context switch. Okay. And then again, after some times, it may get the CPU. and it may execute for the remaining 4 milliseconds, because each time interval contains 6 milliseconds. In the second case, it will complete by the once it by the end of the second part of the fourth millisecond, it will finish. If the time quantum is only 1 millisecond, that is after every 1 millisecond, the CPU is going to context switch. In this case, what happens? There will be, so here the number of, in the second case, the number of context switch is 1. In the third case, if the quantum value is reduced to 1, then first the CPU will execute this process for 1 millisecond, then there will be a context switch. After sometimes it may get, then again it will be using only for 1 millisecond, then there will be a context switch. Like that it will be doing. So entirely, totally it needs 10 milliseconds. So to complete a job of 10 millisecond time, there will be 9 context switches, okay, which is very high. And also it increases this process overhead, CPU overhead. So identifying the correct value for Q is a crucial thing when you are working with round robin